Hi, I am Daniele Santoro from the Cybersecurity Center of the Bruno Kessler Foundation, and I'm going to present a demonstration of the work Cloud Native Cyber Deception with Decepto. Let me short introduce first what cyber deception is. It is a well-established cybersecurity strategy that consists of creating deceptive elements in a network, call it decoys or honeypots, to mislead and divert potential attackers. But nowadays, when it comes to cloud-native environments, current solutions either augment the implementation of a specific microservices-based application to serve as decoy, or entirely clone it on a separate environment. For this reason, we propose a new solution with three main goals. Increase the decoy credibility. They appear to be genuine assets as they are melted down within the production environment. Being resource aware, the idea is that we can lower down the cyber deception requirements because just a subset of microservices composing the application can be cloned as decoy. And finally, automate and generalize the decoys creation and deployment processes by leveraging the Kubernetes functionalities. So, Decepto is proposed as a software platform to integrate cyber deception within cloud-native application. Decepto has two main components. The decoy placer on the top, which is the mind of the system, can support different algorithms, and its role is to choose the set of microservices to clone as decoys, for example, based on optimization metrics such as availability of resources. And then Decepto in the bottom, which is the arm of the system. It is a custom Kubernetes controller providing innovative features and extending the cluster with a new custom resource definition, the so-called app graph. Using an app graph, a given cloud-native application is modeled as a graph of microservices and data flows. The main idea is that microservices can be cloned independently to behave as decoys. The cloned pod is instrumented with capabilities to discover and monitor an attacker, and it is purged from any dependency it has with the legitimate microservices. By means of network rules, application-level isolation is enforced, thus decoys cannot interact with legitimate microservices. As a demo playground, we use Online Boutique, a web-based e-commerce application used also by Google for demonstration and testing purposes, which consists of 11 different microservices. The demonstration is showcased in three phases presented in this slide. The first phase is about initializing the cyber deception feature on a given application by creating a dedicated custom resource definition in the Kubernetes cluster. In the second, a proactive decoy creation is activated by the decoy placer, which, relying on internal algorithms, suggests to clone two legitimate microservices as decoys, AD service and checkout service. The third phase, instead, is about reactive decoy creation. Indeed, we simulate a lateral movement from a compromised front-end microservice, and we let Decepto to firstly intercept it, and secondly, take some corrective actions, for example, creating additional decoys to divert the attacker. But let's now move to the real demonstration. On the left of the screen, you can see in a browser the main page of the Online Boutique application, exposed by the front-end microservice. The service has been modified by us in order to expose a vulnerability that we will exploit later in the demo. On this tab instead, we see the Decepto GUI, which is empty because the system is not yet active. The terminal on the right side will be used to show Decepto logs and to interact with the Kubernetes cluster and with the demo. You currently see all the 11 microservices of the Online Boutique application safely running in the cluster. Let's start with the initialization phase. To activate the Decepto on the application, we need an app graph. Since no app graph are present, we will install one. I remind you that the app graph is nothing else than a CRD, so custom resource definition, describing your application by means of microservices and data flows across them. You see on the Decepto log and also in the GUI that this custom resource definition triggered the activation of the second phase, the proactive cyber deception, which proactively instantiates two new decoys by cloning legitimate services. Indeed, AD service and checkout service are created. These services are composed by three containers: the legitimate one, the monitor, and the sentinel, as you can see here. The monitor saves network traces for a given decoys, while the sentinel is listening for incoming and unwanted connection on it. These decoys, and in particular the checkout service decoy, is also advertised in the Kubernetes service discovery, but its communication are controlled by network policies in order to prevent, for example, any communication from it to a legitimate microservice. In the current status, we allow an hypothetical attacker to interact with our decoys, and we are just waiting for the attacker to make a misstep. Let me now impersonate an attacker that successfully compromised the front-end microservice. I will use the shell on the top in order to receive a connection back from the attacked service, and the one at the bottom in order to perform the real attack. We just need to execute the attack and then stabilize the shell in the channel, like this. And here we go. We have a reverse shell on the front-end container, and we can evidence of it by asking for its hostname. This attack is a carriage return line feed, and details can be found in the Decepto code and Decepto documentation. Now, what an attacker would most probably try to do is to find additional and more interesting targets. For example, starting a malicious script downloaded from a remote source to discover them. In the background, the script is enumerating all the possible discovered services, and indeed, it will find also our two decoys. With the next command, I will try to contact the decoy, and you will see additional reaction. This container should not receive traffic at all, because it is a decoy. So when the Sentinel sidecar in the decoy notices that there is unwanted communication, it raise an alert that can also be seen in the GUI. As soon as the lateral movement is captured by Decepto, it reacts by cloning additional microservices. The main idea is that part of the decoys are created upfront, while others can be cloned in a reactive way only when the application is under attack, and only on certain part of the application graph, which are considered compromised. To conclude, let me share a pointer to the project, which is open source. In the demonstration, I didn't deep dive into some details, but you may find all the information on the documentation page. And if not, just send me an email. Thank you.